Okay, we'll go ahead and get started. Good morning, I'm Greg Conti. This is Sergey Bratus, and we've been taking a very hard look at inside binaries, inside binary objects, whether they be memory dumps, files, file systems, anywhere we find zeros and ones. And what we found is a great deal of structure, a great diversity of binary species, and I think the understanding of that will help you, whether you're a forensics engineer, a reverse engineer, a fuzzer, or a security researcher in general, understanding the building blocks of these binary objects, something that's between the data type, ints and longs and chars and all of that, and the object itself, a Word document, a binary Word document or something. So we're going to focus, we've tried to document as many of these types as possible, put them into categories. We have ways in the talk to visually identify them, as well as statistically to identify them, so it can ideally be automated. And the ultimate goal is to help you do your jobs better, speed analysis, and gain insight.
Well, I have a bit of a personal history here. Greg was the one who put me up to it. He got me interested in visualization, in leveraging the power of just the naked eye when looking at the bits. Because when you get to see those bits flying by or scrolling by on the screen, you sort of kind of see the patterns, and you actually get to recognize the patterns. And if you shift the data around, then you see the patterns in the shifting. But all of this is tantalizingly close, and yet really hard to actually use. So what we're trying to present today is ways to actually make it simpler and isolate a few visual primitives that will hopefully tell something useful about a piece of a binary at a glance, and give you a reference as to what this thing might be. It's not something that you wouldn't be able to do with more advanced tools or special scripts, but those things will cost you. Those things will cost you the time to run them, the time to pre-process the data. Here, the idea is to have a visual cue that's just right there, and to switch between those visual cues very, very fast.
Okay, good. For bonus points, who's the picture, the bug-eyed man in the picture? Charles Darwin, very good. They had some great photographs. So this is my disclaimer. Does anyone read Rot 13 natively? I know no one reads it anyway, so I thought I'd make it Rot 13.
Что это значит?
So anyway, we're here as free citizens and not the representatives of our employers. So we're going to be using several visualizations, this one most of all. If you think of any binary object, whether it be memory, network flow, a file system, it consists of numbers, zeros and ones, or bytes. So if you think of that sequence of bytes, in this example, 255, 108, 40, and so on, and you plot those into a graphical window from left to right. So the first byte in the file is the top left corner, the second byte in the file is the next byte to the right, and the third byte, and so on. And what we've done is mapped the color, the grayscale, to the byte value. So 0 is black, 255 is bright white, other byte values are shades in between. And the advantage there is you can play with these color mappings and do all sorts of things. But the idea is this allows you, when you compare a hex editor's window to a graphical window, you can see about 300 times more information, at least in a graphical way. Obviously a hex editor shows it in a textual way. But that allows you to see the structure. So let's take a look. So this is a Word document. I've snipped out 10 megs in the middle because I'll walk through. So at the top, that's where a Word 2003 document, that's what ASCII text looks like. The next region is a data structure, and then the white noise area in the middle is several compressed images. And if you look where that black line in the middle, the actual header, the data structure that's the header for each embedded image is visible between them. And then at the end, you see other structure. And for example, there's a table of Unicode URLs that are in the document and other data structures in there. The idea being, and it goes back to what I said at the beginning, that there's integers and longs and chars, and then there's Word documents. But really, these things, these jar files, these executables are all built upon these primitive fragments, these primitive types. That's what we're calling them. Things that are bigger than the basic programming data type, but smaller than, say, a container object. And let's just look at an example. So this tool should be on, we submitted it should be on your CD, although we have not checked. And it allows you to load the file and bring it up. So here, this is shell 32, DLL. And you can adjust the width as you see fit, and it'll resize it. So you can get to like an offset that makes, or a window size that makes sense, like the different data structures in there. And then you can play through it and see the various structures. At this point in the talk, don't worry about what these structures are. We're going to go through that. But the idea being just that there are numerous structures inside a file, and it's good to know what they are and know what they look like and so on. And then you can scroll through and so on. So anyway, yes, Sergey.
So if I may jump in at this point. It's really interesting how the structure of binary files is being completely ignored everywhere you go to get an undergraduate CS education. So how many different sections do you expect to find in your typical Unix utility?
Like
1, 2, 3, 4, 5.
You mean ELF file?
Right?
ELF?
Yeah. Let's say ELF, right?
I'll go for 4.
32. Thank you. 32. These are 32. So obviously there is text and data and some sort of a header, right? So you can find 4 quite easily. But in fact, if you look from section to section, if you look at the section table, in the modern 32-bit, 64-bit machine, you will find about 32 sections in there. Some of those are symbol tables. The dynamic symbol tables account for at least 10 of those sections, all the sections that work together to give the dynamic linker that which it uses to link in the libraries. The symbol table, the string table, so some of the ASCII that you see as you scroll in there, and as you will see with the binviz tool. Then possibly even a hash table for lookups. But there are 32 different kinds of data that are different enough semantically that they have an entry into that table for their own. Just think about that, right? They are, well, some of them are code. Some of them are code that only works with this little bit of data, like the procedure linkage table that works with the global offset table. And the dynamic linker stitches this up when called. But there is a lot of diversity, even within a single executable file. There will be even more in the memory image when that file is loaded and executing.
So, and just have some other examples. This is a jar file. And again, don't worry about what the structures are. Just note that there are different ones. This is an executable that Sergey was just discussing.
And we can actually see some of those sections right here. So this is the ELF header. What comes next is the section table. It's right there in, and it's it's offsets into the file, packed close together. Then you will see code, and you will see data, and hopefully most of this is code. But there are also strings that go into dynamically linking the file, and there are all sorts of versioning information. And if your executable is not stripped, then there's a symbol table and other kind of debugging information closer to the end. But all of those things, I mean, these are 30 to 32 sections laid out, and you can actually make them out very easily. And you can actually make them out even more easily before the file has been linked together, because you've got runs of zeros where the addresses of the functions would go. So,
and the same goes for system memory. This is from the Digital Forensics Research Workshop data set that they released this year. It's a Sony Ericsson K800. It's just a snippet from memory. And even network traffic, right? So this is a byte plot, but except that it shows one packet per line and kind of does a carriage return. So the long lines were large packets, the short lines are small packets. But again, this structure exists. And that we argue the current tools, things like grep and strings, hex editors for this general purpose problem, just they're insufficient. We can do better, and that's what we're trying to get at. And alluded to this at the beginning, that you're going to encounter unknown, unfamiliar structures. Typically, you'll be looking at them in text. And what we're trying to do by getting our arms around all the various types of building blocks, primitive types out there, we can help facilitate deep understanding, help you as a reverser, as a fuzzer, as a forensics analyst. And we're working on something called memory mapping. And the idea is if you can programmatically identify each of these primitive types, then you can write a program that dumps out. And here's an example. This is a memory map. Not the binary mapping. For bonus points, what is this the memory map of? I heard Commodore 64. This is Commodore 64 memory map, but it was the intuition.
Glorious 8-bit address
yes,
space.
Beautiful. So the idea, though, and so from that memory map to this idea of binary mapping, that if you have the ability, then if you understand what these fragment types are, or primitive types are, you can identify where they begin and end within a file, and from there you can toggle them on and off and say, only show me text, or I don't care about text, or show me only code, or I don't care about code, and slice through the file, removing a layer at a time of this unknown thing you're trying to analyze. That's the idea. Another idea is that you can embed, we get our arms around this, we can embed it in things like a hex editor or mocked up there's a strings tab within IDA. You could have a compressed tab, an encoded tab, bitmap, audio, as you have this ability to identify these things. This is a taxonomy. It's the tree of programming languages. And I thought it was very useful to just show that this thing could grow without bounds. There's many, many different interpretations or variations of binary, of primitive types. So the idea then is we had to draw our arms around it and kind of scope what we did. Otherwise, it would spiral off into this incredibly unsolvable problem. So what we've done is kind of define the root of the tree and of things that you're likely to encounter, and went into a certain level of depth here and more depth in the white paper that we released. Okay.
So I would like to make a disclaimer. It's impossible by looking at a run of bytes to tell what those what those bytes are, what they do, what format they belong to. It's really, really very, very hard, and it's provably hard. Okay. However, most of the time we are not looking at those incredibly disguised things such as shellcode that is supposed to be the English text. Such a thing has been done. We'll mention it as we bow out. But most of the time, you want to know what the hell is it that you're looking at. Is that a compressed stretch of bytes? Is that something that might be media? Is that something that's likely to be code? So, one of the great things about IDA is that, well, it's interactive, right? You get some heuristics to actually try to guess what a segment is, and then if you didn't guess right, you can annotate it as code, and you will have a disassembler run over it and do the smart thing. But wouldn't it be nice if you could say, here is something that I think is compressed with oh gzip or with oh